Here's a vertical curve example. A classic one that I call is the pipe problem. So we have a sag vertical curve with equal tangents, and it's joining a 1.2% negative grade with a plus 0.8% positive grade. The PVI of the vertical curve is located at station 75 plus 00, and the elevation of the PVI point down here at the intersection is 150 feet. There is a pipe crossing the roadway located at station 75 plus 40, so that's just 40 feet downstream of the PVI. And we're told that the top of the pipe elevation is located at elevation 152. So we have the elevation of the top of the pipe. And the center line of the finished roadway, we must have three feet of clearance from the finished road to the top of the pipe elevation. So the typical question that we're asking in a problem like this is, what is the length of the vertical curve that will satisfy these constraints? Here we go. So I've extended the tangent. As you can see, the green line extends the tangent 40 feet. So I can calculate the elevation of the point on the tangent at station 75 plus 40, which is just 150, which was this elevation, minus 1.2% times 40 feet in order to get the elevation here. So we can calculate that that is equal to 149.52. So we know the elevation of the top of the pipe is 152, and then we know that the elevation at the finished grade is 155. So I've also drawn this orange triangle here, this one, like this. So it intersects the curve at its finished location, and actually, if you notice, we know this total distance. So we're going to use that knowledge of the triangle in order to solve. So I've added a few labels to the diagram now. So what I'm calling y is the distance between the finished roadway at 155 and the elevation on the extended tangent at 149.52. So I just calculate that that value of y is 5.48 feet. We know that L over 2 is between the PVC and the PVI, and we know that 40 feet is the distance from the PVI to the pipe. And so this, what I've called x, which is this total horizontal distance here, is just L over 2 plus 40. So if you look at the orange triangle, we have now the two of the sides, the horizontal component and the vertical component. So we're going to use this information to back out the required length of the vertical curve using the quadratic formula. So in order to do that, we first calculate A, which is just the absolute value of G2 minus G1. In this case, it's plus 0.8 minus 1.2, and that turned out to be 2. So we know that the offset at any location x, so the offset we call y, we have that value because we found that that value is 5.48 feet. So we can set that equal to ax squared over 200L, and we can start inserting the elements that we know. And we know in this case that x is L over 2 plus 40 from before, and so that is squared multiplied by 2 divided by 200L, and that's this line. And then in the next line I'm just simplifying, so I've multiplied out the square, and I'm just reorganizing the equation in order to get a nice equation here, L squared minus 2032L plus 6400 equals 0. So prove to yourself that you can do that algebraic adjustment. And then, of course, you could go to your calculator or to a math.com website and solve this quadratic formula. But just for fun, I'm going to remind you of what that formula is, as shown here, negative b plus or minus the square root of b squared minus 4ac over 2a. So say that 10 times fast. And then I'm just inserting the variables into this equation. And then what we end up with are two possible values for L, the length of the vertical curve, either 2029 or 3.15. We can immediately discard the value of 3.15 since it's way too small. And so we know in the end that the length of this vertical curve needs to be about 2,029 feet. I would probably round up and say 2,030 feet. By calculating since we already know the station and elevation at the PVI, all we want to do to complete the problem is calculate the station and elevation at the PVC. So I've done this in this graphic. We use L over 2, and we use the slopes. So the elevation of the PVC is 150 plus L over 2 times the slope of 1.2%, so that's 162.17 at the PVC. And the stationing is just 75 plus 00 minus L over 2, so then the station there is going to be 64 plus 85.5. And the similar procedure that we follow for the PVT over on the right, we take the elevation, 150 plus L over 2 times the slope of 0.8 multiplied by 0.008. So the elevation at the PVT is 158.12. And the stationing is just 75 plus 00 plus L over 2, or 85.14.5. So we're done. Thank you very much.